You are sitting across from the examiner in your final oral boards. The question sounds simple. Explain the changes in dynamic compliance with the application of CPAP in normal lungs. The immediate clinical instinct is to say that continuous positive airway pressure improves compliance. You apply positive pressure, alveoli open up, and the lungs become easier to ventilate. But answering that way guarantees a failing grade. The trap lies entirely in the last two words of the prompt, normal lungs. That clinical intuition is built on treating sick patients. To pass the exam, you have to discard your hospital experience and rely strictly on physical modeling. Dynamic compliance equals tidal volume divided by the difference between peak inspiratory pressure and positive end expiratory pressure. This driving pressure fights two physical forces, inward elastic recoil and frictional airway resistance. To answer the examiner correctly, we have to calculate exactly how applying continuous positive pressure alters the net sum of those two forces in a healthy patient. This graph is the sigmoid pressure volume curve, mapping pulmonary mechanics. It dictates the pressure required to inflate the lung. The curve has three zones: a flat atelectatic bottom, a steep compliant middle, and a flat over-distended top. After a normal expiration, the remaining gas volume is the functional residual capacity, or FRC. In a physiologically normal lung, FRC maps to the exact center of the steep linear portion of this curve. This position represents perfect mechanical equilibrium. The inward elastic recoil of the lung parenchyma is exactly balanced by the outward recoil of the chest wall. Because the operating point sits on the steepest gradient, a very small change in driving pressure generates a massive tidal volume. The normal lung at resting volume is already operating at peak efficiency. It requires no mechanical assistance to optimize its stretch. When we apply continuous positive airway pressure to this healthy lung, the constant pressure artificially elevates the baseline FRC. This shifts the operating point up and out of the steep compliant zone, driving it toward the curve's upper inflection point. At this high volume, the alveolar walls are stretched to their absolute elastic limit. The tissue is completely taut before inspiration even begins. Inflating it further incurs an elastic penalty. Expanding stiff tissue requires exponentially more energy. Looking back at the chart, you can see the mathematical outcome. Up here, generating that same standard tidal volume now demands a massive increase in driving pressure. By forcing an optimized lung into alveolar overdistension, the positive pressure destroys the system's elastic efficiency. An examiner will ask, doesn't positive pressure splint airways open, reducing resistance and improving compliance? Physiologically, this premise is true. At higher lung volumes, radial traction from the surrounding tissue physically pulls the smaller airways open. Following Poissol's equation, as the radius of the airway increases, frictional resistance to gas flow drops exponentially. But the argument collapses when you examine the scale of the variables. In a healthy airway, baseline resistance is already extremely low. The fractional gain of dilating a normal bronchioles is marginal compared to the massive energy penalty of pushing alveoli to their structural limits. Dynamic compliance is a zero-sum equation. Restrictive and elastic forces compete to define the final volume. The drastic increase in required driving pressure needed to overcome the stiffened alveoli swallows the tiny reduction in airway resistance. The severe mechanical disadvantage of elastic overdistension outweighs the resistive benefit, resulting in a net reduction in dynamic compliance. We can solidify this answer by bringing in time constants, which equal resistance multiplied by compliance. Dynamic compliance is frequency dependent. Higher respiratory rates leave less time for gas to equilibrate across different lung units. Stiffened, over-distended alveoli interact poorly with rapid inspiratory flow rates, worsening the dynamic measurement even further. Finally, we must look beyond the lung parenchyma itself to the outer boundary of the system, the chest wall. The continuous positive pressure physically flattens the diaphragm and artificially expands the ribcage. This forces respiratory muscles to contract from a shortened resting length, creating a severe mechanical disadvantage. Total respiratory system compliance requires factoring in both the lung and the chest wall. Ultimately, applying continuous pressure to a normal patient actively sabotages the mechanical efficiency of the entire thoracic pump. If the physics dictate a negative outcome, why do so many candidates intuitively believe the opposite? Because clinical intuition is shaped by treating disease, not by observing health. Compare our normal model on the left to an ARDS curve on the right. In ARDS, resting volume sits at the flattened bottom. Applying positive pressure recruits collapsed alveoli, pushing the operating point into the steep compliance zone. The physiological response to positive airway pressure completely inverts depending on the baseline condition. It saves the diseased lung precisely by doing the opposite of what it does to the normal lung. We can now return to the examiner's trap, break down the physical mechanics, and dismantle it. Step 1. A normal lung operates at peak compliance at its natural resting volume. Step 2. Adding continuous pressure artificially elevates that volume, pushing the alveoli to their upper elastic limit and inducing overdistension. Step 3. The resulting elastic penalty requires massive driving pressure, easily overriding minor reductions in airway resistance. In physiologically normal lungs, applying continuous positive airway pressure definitively decreases dynamic compliance. Understand the baseline, do the math, and you will pass.